Okay, starting a little bit of our new chapter, aqueous solutions. We kind of talked about aqueous solutions a little bit, but we're going to talk about them in more detail, and we're going to give you some math to use with aqueous solutions. So you may know some things are soluble, some things are not soluble when you try to dissolve them, for example, into water. We looked at some examples of that at the end of last chapter. There's a definition for solubility. Solubility is the amount of compound that dissolves in a certain amount of liquid. And there's different units that you'll see for this, but it's usually an amount of a compound in grams, and it's often also an amount in grams for whatever the solvent is. So for example, table salt, you can dissolve 36 grams of NaCl in 100 grams or 100 milliliters, they're about the same, of water. If we are at this limit, this is the maximum amount that you can put in, so you wouldn't be able to get 37 or 38 under normal conditions. You could get up to 36 grams. If we were at 36 grams of salt per 100 grams of water, we're at our limit, then we call that a saturated solution. So no more solute, our minority component, our non-liquid component often, no more solute will dissolve. If you try to add extra solute, it will just stay floating around as a solid, usually at the bottom. There's also cases where we'll have less than that solubility amount, and we would call that an unsaturated solution. It's not saturated. It has room to dissolve more. Solute. So saturated is when we're at our limit. Unsaturated is below our limit. We also have supersaturated. So despite what we said about saturated being our limit, we can actually exceed our limit, just not for very long. So a supersaturated solution is more than the solubility amount. Or more than the solubility limit. And because it's more than the solubility limit, supersaturated solutions will normally precipitate. So you'll have a solid that forms. Just leave them out at room temperature and they'll form crystals, or cool them down and they'll form crystals. Get rid of some of the solvent and they'll form crystals. We used this to our advantage in the alum lab. That's how we were able to produce crystals. Supersaturated solutions also form under specific circumstances. I'm saying specific instead of special because opening a can of soda is typically at like about 2 atmospheres of pressure. When you open it up, the pressure drops to the atmospheric pressure, which is about 1 here. And so carbon dioxide, CO2 gas, bubbles out of soda when you open it up because we've dropped the pressure and changed the circumstances. There's some video link examples here that I can't show you because I think it'll crash the presentation. But supersaturated solutions are unstable, and sodium acetate or ammonium nitrate can form fun, very rapid, sometimes jagged crystals from a supersaturated solution. There's a temperature dependence for most things with solubility. The general rule of thumb is that solids are more soluble at higher temperature. The relationship is not always the same, so what we're looking at here on this graph, our y-axis is temperature, so moving from left to right, we're increasing the temperature. And then our solubility is on the y-axis, so if we're moving up on our y-axis, that's increasing our solubility. You'll notice that for most of these lines, except for the SO2, for most of these lines, our line goes up as we move left to right. That means our solubility is increasing as our temperature is increasing. Again, this is just the general rule of thumb. It's not always the case. Right, so SO2 here is an example of that not being true. But generally, you increase the temperature, you increase the solubility for solids. And one application of this, sugar dissolves more easily in hot tea than in iced tea. So if you're making iced sweet tea, dissolve your sugar first while it's hot before you cool it down, and it'll dissolve in easier versus if you try to add sugar to iced tea, it's not going to go in quite as well. We can also take advantage of this trend to do recrystallization, reforming crystals of a solid. So to do recrystallization, you prepare a saturated solution at an elevated temperature. And the reason that we do this is at the higher temperature, solubility is higher. As we cool down our solution, our solubility decreases. So solubility decreases as temperature drops. So we were at this high level of solubility. Show that on the graph. So like if we have this KNO3, if we prepare a saturated solution at this temperature, at this point, and then we bring the temperature down, moving to the left, our solubility will drop. So let's say that we cool it down to here. We've lost all of this solubility. So now we would be supersaturated because we have this much dissolved, but we can only have this much dissolved. And so our solubility dropping, that's going to cause us to have a supersaturated solution. And so some of our solid will precipitate. And typically when solids precipitate out again, they'll form crystals. And the slower that they form, if they form slow enough, they'll form as really nice, clear crystals. And they'll also tend to reject impurities. So other things that might have been in your original solid will also get rejected. So this is one method of purifying solids. And it's one that you can also try at home with some possibly very tasty results. So you can use recrystallization to your benefit to make rock candy at home. The way that you would probably do this, if you want to try it, you'd prepare a saturated solution. So you'd heat water, add a ton of sugar, not a literal ton of sugar. Stir it until it won't dissolve anymore. And then you can transfer it to another container. It's like if you were heating it up in a pot on the stove. Transfer it to another container, like a Yeti if you've got one that you can do this with, or just a canning jar. And then you can put like a popsicle stick with a string on it, or you could dip like a wooden stick like they often sell rock candy on, and crystals will form on it over time. I don't know how to draw crystals, so I'm just going to make them green. They shouldn't be green unless you add green food coloring. So you can leave it to cool. The slower that it cools down, the longer the time you give it, the better the crystals will come out. and eventually at the end you should be left with nice sugar lumps, ideally on your string, and then you can eat them as a snack. So this is something that I recommend you try at home. I have yet to have a student send me an example of, hey, I did it, but I'd love to see it if you try it. So please do. Gases can also form solutions in water. An example of this being a can of soda. A can of soda has carbon dioxide, CO2, that's the bubbles, dissolved in water. Most liquids, nearly all liquids, have some dissolved gases. If you drink water from a well, there's a good chance that you've got a lot of dissolved gases in there. Like you might even be able to see them coming out as you're, it's just coming out of the tap. So we can also have solutions of gases in water. Lake water and seawater contain dissolved oxygen that fish need to breathe. So that's often why you'll have like a pump or a bubbler in a fish tank. It's so that the fish can breathe. If you don't do that, they have to come up to the surface to try to breathe air, or they just suffocate, which is not fun, I imagine. Gases also have a solubility relationship with temperature. So the solubility of gases decreases with increased temperature. So this is the reason that if you open up a can of soda that's warm, it should fizz more than a cold can of soda. It'll also go flat faster than a cold can of soda. And on our graph here, we've got, again, temperature on the x-axis. We've got a bunch of different gases. We've got solubility on the y-axis. We can see that as we move left to right, increasing temperature, all of these solubility lines are decreasing, so we've got lower solubility at higher temperature. The way that I like to think about solubility of gases and solids in a liquid is if we arrange, we'll do a separate thing here. We arrange our states of matter. What's our lowest temperature state of matter? Solid, liquid, or gas? Solid. What's our middlest state of matter? Liquid. And what's our hottest state of matter? Gas. Gas, notably very hot. Okay, so if we want a solid to become more like a liquid, how would we get a solid to become more like a liquid with temperature? We increase temperature. So increasing T makes it more like a liquid. Since it's more like a liquid, the solubility increases. That's our trend for solids and gas, or solids and liquids for solubility. If we want to make a gas more like a liquid, to dissolve more in a liquid, what do we do with temperature? Decrease it. It's the opposite thing. So it's more like a liquid as temperature drops. So for our temperature graph here, right, if we go from 30 to 10, our solubility increases for all these gases because they're becoming more like a liquid. They're more easily able to interact with the liquid and stay in solution. So I think that's a nice way of thinking about it if you can hold that in your brain. Or you can also remember solubility for solids is what we would expect, increased temperature. For gases, it's the opposite. So either of those two methods work. Questions? Okay, that'll do it.